replace this loss function with another loss function that is the sum over the samples. And when the samples are few, the approximation can be very bad. And so what you learn by minimizing the sum over the sample can be very far from what you can obtain by optimizing over the true loss function. That is inaccessible to you, because you do not know. Is that clear? Are you following or not? Now is the moment to stop me. Yeah?
I understand what you're saying. You don't know the underlying. You don't know the underlying distribution. Right?
No.
So, are you still going to use the squared error, just replacing by the sum? Can you make it?
Yeah, actually we will see this later on. But what I'm anticipating now is that this integral, that cannot be computed because we do not know P, will be replaced by taking samples from P that are the samples where you are learning from. And so the integral becomes a summation where the value of x and t are the values that you see in the samples. So this the integral is a summation of a continuous.
Sure, but can you still do that, not knowing the underlying distribution?
You are assuming that the samples comes from P. And so if you have infinite samples, actually this summation converges to this integral. So it's sound. The problem is that when you have a few samples, that the summation is that can be a bad approximation of what you want to learn. Especially, and then we will see, if you consider for y a very large hypothesis space. Okay, now
Quando dice summation intende la sommatoria.
we have said,
Divisione.
okay,
Perché l'ambito è moltiplicato
we
per
are
due.
not obliged to have a model that is linear in x. We need only, for using linear regression, to have a model that is linear in the parameters w. So what means? It means that instead of writing the scalar product between w, the parameter, and x, the input variables, you can take the scalar product between w and phi of x. That is any function phi that you want, any vectorial function phi. What means?
Thank you.
So, suppose that you start from an input space x. This is the input space. Suppose that you have two input variables, x1 and x2. Okay? These are your input information. Let's make an example. Suppose that we want to predict the weight of a person, knowing the age and the height of the person. So suppose that x1 is the age and x2 is the height. Okay? And so what happens? And what you want to predict, so t is the weight. So now you collect some data. So you go to different persons, okay, you ask the age, you ask the height, and then ask also the weight. Okay, and you collect samples of this kind. Now, what's the problem? The problem is that, let's focus on the height. Suppose that you have a linear model. Is the weight a linear function of the height? If we were one-dimensional objects, probably yes. But since we are three-dimensional objects, it's difficult that. So, for instance, my daughter is half of my height, more or less, but is 15 kilos, and I'm not 30 kilos. So, probably a linear model between height and weight is not a very good model, right? But no problem. You can change the input space and move into a feature space that is obtained by combining the input data inside. For instance, suppose that you are not happy with this kind of input space, and so you build new features. So here you start from an R square space. You want to move to a feature space that can have many more dimensions than X, or less, but different. For instance, suppose that instead of having only age and weight, I want to put here also, I want to have weight, okay, I want to have age, okay, I want also to have weight square, I want also to have weight cube, because you have three-dimensional objects, so it's more or less reasonable that there is a cubic relationship between the height and the weight. Perfectly proportional when we grow, more or less. Okay, and maybe I want also to put something that takes into, sorry, I have written weight, but of course it was height. And maybe I want to put another feature that is age times height, or whatever you want, actually. So what happens is that given a point here in a two-dimensional space, I can build some transformation that brings me to a new point here in this 1, 2, 3, 4, 5-dimensional space. And of course, all these values can be computed starting from these two values, because they are only transformation of the original information. So what I'm doing is that I have an input space of 2 dimensions, but using the function phi, I can project this point in a different dimensional space, usually with more dimension, but you can do whatever you want, okay? By transforming this data in something that is more useful for my problem. Phi encodes what is called the feature engineering of the problem. So you want to build features that are related to what? To the target variable weight. So actually, phi is a function that takes, in this case, as input a 2-dimensional vector and produces as output a 5-dimensional vector. And now you see that now the summation is no more from 1 to d minus 1, but it's from 1 to m minus 1. So here we have the d was equal to, in this case, d was equal to 3. Remember, because the input space has size 2, but the d was the number of parameters. So you have also parameters of the intercept. So they are 3. So d is equal to 3, while here m is equal to 6. Okay? Because there is also the parameter w0 that you have to consider. Okay? So this just to say that if now, suppose that now I plot only, here I put weight, and here I put height. So height as input, weight as output. Okay? And I see samples here. And the samples suppose that are distributed to something like this. Okay? Now, if you use linear models that are linear also in the height, you can only represent something like this. But if you are changing the input And instead of having height, there you put height at cube. What happens? Suppose that here instead of height I put height at cube. If it's true that the height, the weight, is a cubic function of the height, how are the points disposed in this frame? Linearly. And so now what happens? That now a linear model with this input space is perfectly able to learn your system because you have changed the coordinates. And you have found the coordinate frame where your data linearly positioned with respect to the target variable. And so now a linear model can effectively learn what you want. You have transformed the space, hoping that points displaced over a hyperplane. This is the idea. So again, here you have the model. You have n parameters for n minus 1 features. And your model is again a linear model of this new feature. Of course, the features can be nonlinear function of the input variable. And so this means that the linear model can learn nonlinear function of the input variables. Right? Because having you transformed the input variables with nonlinear function, now the models that you learn is no more linear. Because if now I plot this linear model here, in this space here, what I get? I get this. So this linear model is non-linear in the input space, where the input space has height and not height at cube as a feature. Yep. Yeah. Yeah. To learn nonlinear models of the input variables. This is the idea. Of course, if you do not do this, you can learn only linear function of the input variables. But maybe in your case, your data are not linearly distributed. And so you need to change the input space so that in this new input space, the data are linear. Now it's an example.
In the input space.
Of course, the feature can be anything that you want. Like in this case, I have used what? I have used polynomial features. These are polynomial features, so where you take input variables and you raise at some power these variables. And you can see what happens by changing the power. You can use, another common choice is to use Gaussian features. Okay, when you take variables and you make them go to Gaussian. To have some other transformation. Or you can have this kind of feature that are sigmoidal. So they are common ways of transforming input data into something else. Again, with which goal? With the goal of hoping that the data will go over an hyperplane. Because you are capturing the nonlinearities in the function model inside the features. So that you can use simple linear parametric models to learn the target function. Here is the example. So here you have the original data. So X is the original input data, T is the output data. And if you use linear model in this space, you have only lines. And you can see that lines are not well suited for the sample blue points that are not linearly distributed with respect to X. Now, this is the model that fits. And you can see that the red line that best fits this data is not linear with respect to X. But these are the data if you consider how they are distributed with respect to X squared. These blue points are the same here and here are the same. They have simply reshaped by changing X with X squared. Of course, they moves clearly. But you can see that now, again, they are not linearly distributing even with respect to x squared. But it's something better than with respect to x. The good thing is that if now you take x squared and x together, so now the feature space is made by what? By x, x squared, and the constant term. What you get is the following. So here in the input space you have x, you have x squared, and you have t. And I have rotated the view so as to show you that now these points that are always the same point in this space are all along, small noise, along an hyperplane. What means this? It means that a linear model here sucks. A linear model here sucks. A linear model here is quite perfect. And you have simply transformed the input space. And this can be extended with many now, okay, it's a simple square model. But even if you have a sinusoidal or not continuous model in the original input space, if you are able to find very good features, so how to transform the original features in new features, you can be able to learn linear models in this new feature space that can learn perfectly your technique.
In your it's the case where in the model you're going to have f equals beta 1 times x squared for it. That's what you're doing.
Yeah, this plane is obtained by computing y equal to w0 plus w1 times x plus w2 times x squared. And then by making it learn w0, w1, and w2. But the model is linear because w0, w1, and w2 are linear. X squared is a feature. But you do not need, for doing linear regression, you do not need to have features linear in the input space. You can use features whatever you want. And so one could say, okay, I have solved the problem. I take one variable and I produce infinity. I do Fourier Basel expansion. I build all the polynomials in the world. What's the problem? So I have a universal approximation. You are right. The problem comes with this. If you have a few data, you can build whatever series expansion that you want, but you will get rubbish from that. Okay? Yeah? Yeah. Transform the input to linear.
Starting from S, transformation and obtain something that is linear in another.
Okay, you are saying it is only possible to find a transformation that maps to linear. The answer is yes. And the answer is very easy. The way is very easy. Suppose that you know the target function. You build only one function that is the target function, and you place weight 1 to this function. Of course, you need an oracle to do this, but it's always possible. The problem is that usually you have no clue how to do this, because if you are able to do this, it means that you know the solution. So usually what you do, you do exactly what is here. You start from a small to the linear feature, and then you try to expand the feature space, hoping to add in the feature space what means in terms of hypothesis space. So suppose that you have only linear features. You have some hypothesis space. You have linear models with linear features. Then I ask you to, okay, now add some other features. What happens to the hypothesis space? The number of parameters increases, and so the size of the hypothesis space increases. Okay? We have a problem with this. Because, of course, increasing the hypothesis space, there is more chance to find the true model inside your hypothesis space. But the problem is that there is more risk to be sensible to noise and find a very bad solution. Like the interpolating curve that we have seen before. you can always arrive at interpolating your data, but you do not want to interpolate the data because you are learning the noise in that way. You do not want to learn the noise. You want to learn the model. If you have infinite data, the data cancels out the noise. But you have a few data, the noise in the data, and the risk is to learn the noise and not the model. This is the problem. Do you have questions? Yeah. Yes. Actually, all the machine learning is more or less about this, is to learn the basis function. There are many ways to do this. It's not easy, but actually machine learning, the other approaches are other ways of building features in different ways, like neural networks, for instance.
Why not focusing just on polynomials, but using other kinds? Just look at the number of inputs.
Yeah, the problem it's not a problem of. You can also use only polynomials. Nothing bad there. The problem is that many problems may not be the optimal choices because again, maybe with polynomials, in order to be able to model your problem accurately, you need suppose 1,000 features. While using Gaussian, maybe it's enough to use 100. But in other problems, the other way around. So it depends on the problem. Yeah. What?
How do you choose?
This is the funny part. Is the feature engineering part, and this means it's all matter of you, in the sense that it depends, of course. In the case of height and weight, you use common sense. You use, in another case, you use physics. You say, if you are an engineer, you know physics, and so you can write some real problem. You can write equations, and you say, okay, I do not know how to combine, but I know that this feature must be at square, and this other needs to be multiplied by this other one because physics tells. Then physics is not able to say what are the parameters in real life. And so then you fit the parameters in the real data. But the model, the features are given by the knowledge of the problem. If it's a problem where you have not knowledge, it happens a lot of times, okay? Then you go this way. You try. But when you try, as we will see in the next class, you have to be very accurate in not lose yourself. Some good performance that is not real. Because you can always fake yourself by producing very large feature space with very large hypothesis space that obtain zero empirical loss. Very easy. That is not what you want.
The basis function is used to produce.
Can you write?
The basis function is used to produce more information, and at the end it serves to learn the non-linearity of the model. That's it.
What is the subject of the sentence? The subject is
The basis function
the basis function. Yes.
is used to learn the new
Yeah.
the non-linearity.
Actually, the basis function incorporated the non-linearity that you have between the input feature
Okay.
and the target value.
It also can produce new features. That's it.
Okay. Actually, you can produce new feature. You can try with new feature, of course, if you think that you are not capturing the problem. Of course. Yeah.
How do we know what file to use for our input to make the final function linear?
How we?
How we choose the file?
It's always the same question, how we choose the features. The problem is that in some cases you know the problem, so you know what are the features that are important. In the other cases, you have to try with building this series of features. So you take all the polynomials.
Guarda quanto video genere.
But as we will see, you cannot, according to the number of samples that you have a limit in the size of the feature space Because of course, if you have a few data, and you increase the number of features, you are able to find something that interpolates your data that usually is not what you want to do. And so there is a trade-off between accuracy over the training samples and using a hypothesis space that is small enough. Because if you enlarge the hypothesis space by adding features and features, that is what is the temptation that any of you will have. It's not working, then I add new features. Sooner or later it will work. But as we will see, it's just overfitting there. It's not learning. Okay? Okay, see you tomorrow for the thesis.